Our next speaker will be from Venezuela, Dr. Eduardo Greaves, I hope I pronounced that right, on one of the more exciting prospects for future nuclear reactors, the thorium molten salt reactor. Yeah. Well, I'd like to thank the organizers for inviting me to participate here. First, I'd like to acknowledge some of my collaborators, in particular, Sylvie Delpech, with whom I'm working during my sabbatical leave this year in France. And I'd like to dedicate this talk to the memory of Kazuo Furukawa, who was a champion for thorium molten salt reactor, who died just over a year ago. So what am I going to talk about? The problems with nuclear energy technology, the current technology, the thorium molten salt reactor, and some of the various proposals and advantages of the molten salt reactor. And then something of the perspectives worldwide for thorium molten salt reactors. So, what are the problems? The first problem is the non-acceptance by society. After 60 years of development, I will be talking about all of these other points in some slides now. So, the first is the danger of nuclear weapons proliferation. As you see in the top, we use uranium-235 or plutonium-239 in a reactor to produce energy. The rest of the fuel, uranium-238, is a fertile material. With the neutrons, it produces plutonium. And of course, plutonium is very good because it's energy. But it is used for weapons. And a 1,000 megawatt large power plant produces 230 kilograms of plutonium per year. So can you imagine worldwide 1,000 nuclear reactors producing each 230 kilograms of plutonium? It becomes a proliferation nightmare. It's a problem. And it worries people. Another problem is that present reactors, they have the nuclear inside the reactor core, which is like a compressed container at high pressure, very high pressure. And any problem with it is really a deep problem. You know, we saw what happened in Fukushima. And fortunately, none of them actually exploded. None of them actually melted completely. It just a little melting, and it produced enough hydrogen to have the explosions we all saw. So this is a serious accident risk. Then we have current technology. We only use about 1% of the energy contained in the fuel. The fuel is used, it is damaged by the use, by the radiation, and it is exchanged. And it produces nuclear waste. And these elements have to be constructed with extreme care. So it is expensive. And they turn into nuclear waste in 2 or 3 years. And this nuclear waste, if it is not reprocessed, then it is a problem, which we all know. Highly radioactive material with thousands of years of half-life. So now we go to the thorium molten salt reactor, which I call the true green energy system. So What do we want for the world? I think diversity, and nuclear can help to balance. Definitely, we just saw the previous talk. A clean technology, free of CO2, a solution to nuclear waste. We want a safe technology so that we can see the future with optimism, not worry. We want to use our own resources. At least we in the third world countries, we want to control our future and not be subject to policies like the US Global Nuclear Energy Partnership, which puts us as users with no control on our systems. And we want to use our own resources so that we develop, we ourselves, not rely on the development of other countries. And we want to use non-proliferative weapons technology. So, what is the molten salt reactor? I'm going to talk about that after I have a drink of water. It is an idea that occurred to Eugene Wigner and was developed by Alvin Weinberg. Alvin Weinberg, by the way, also developed the current technology we have. The liquid is not solid, the fuel is not solid, it is a liquid. There are no fuel rods. It is a liquid, and the fuel contains in the thorium molten salt reactor mostly thorium, very little uranium. It circulates inside the reactor, and it goes out of the reactor to transport the heat to another cycle, which then transports the heat to the power-producing part. So, why use thorium? Thorium can be used with either plutonium-239, uranium-235, or uranium-233, which is produced by the part of thorium which is inside of a reactor. So this thorium is now substituting for the uranium we had before. And it is fertile. It produces uranium-233, with which you can produce more energy, but it produces no plutonium. Very little plutonium is produced in these reactors. Thorium is 4 times more abundant in the Earth's crust than uranium. So our resources are, shall we say, 4 times 300 years. Immediately we have, without changing very much, the mathematics, 1,000 years of use. It produces much less nuclear waste, a fraction of long-lived actinides. So by fission, you produce nuclear waste, but you also produce actinides, which are long-lived. And in the case of thorium, you produce very little long-lived nuclear waste. And it is a very concentrated kind of fuel. That's an estimation of the amount of thorium needed for the whole life of a human being in a developed society, of course. Now, why liquid fueling? This is again a point. The molten fluoride has a triple function. It is the fuel element to consume and to produce the energy. It is the heat transfer medium, and it is also the fuel processing medium. So you don't have to change things. You can, in the same cycle, you produce the fuel, you transport the heat, and you do the reprocessing. of the fuel. And what is this molten salt? The molten salt is a mixture of fluorides, lithium fluoride and beryllium fluorides. These are salts which are like table salt. It is a solid at room temperature, which at high temperature becomes liquid, and it is clear like water. It is a liquid with very high specific heat and very low viscosity, which is ideal for heat exchange media. It does not suffer any radioactive damage. It is a liquid, and with radiation or with gamma radiation or alpha radiation or neutrons produced, it is not damaged at all. So it remains inside the reactor without being damaged, quite contrary to what happens to solid fuel elements. And it is a good solvent for materials, for fission, for elements of fertile material, and a nuclear property which has very low neutron cross-section. So what does it contain, this liquid? It contains the fuel, which can be uranium tetrafluoride, either as what is used now, uranium-235, or what will be used in the future in these reactors, uranium-233, which is made in the reactor from the thorium. Or it can use plutonium. So the scheme which is thought is to burn all the plutonium in nuclear weapons now as fuel in these reactors, and to use the thorium, which is inside, to be converted to uranium-233, and therefore produce more fuel. So a short history, very quick, of the development of the molten salt reactors. The first idea was in 1954. The Americans had, due to the Cold War, the need to transport nuclear weapons from the US to Russia, very far away. So they asked the Oak Ridge National Laboratory if they could make a reactor that could fly. So it was made, the aircraft reactor experiment. This reactor was the first molten salt reactor, and it worked for 200 hours perfectly all right, and it was light enough to be put in an aircraft, and it gave them the idea to do then a molten salt reactor for power production. And that was the 1965 to 69 molten salt reactor experiment, which had a 4-year operation. And then after that, they created the proposal for the molten salt breeder reactor. And this molten salt breeder reactor was taken by the Japanese groups and developed the Fuji reactor. And further proposals, as shown there, Mozart in Russia, the molten salt fast reactor proposal in France, and several proposals which are now, which I'll mention very briefly at the end. So this is a photo of the molten salt reactor. It was a small thing. You can see this little boy here, which I put there. Standing in here, he would be more or less at the height of this, which was the pump. And this reactor did not produce electricity. All the power was just blown into the air. You can see the diagram in the right side. The reactor was in the middle, and the reactor was stopped every weekend. They drain the liquid to those tanks in the bottom, and on Monday they put it back up and continue the experiment. Very, very different from current reactors, which can't be stopped. So there are several kinds of proposals for molten salt reactors. The first classification is two-fluid reactors or single-fluid reactors. The two-fluid reactors have a core with where the center, here, the reaction takes place, the fission takes place, and the neutrons go out into a blanket which is around, which is there to produce more fuel. So it is a complicated reactor, the core design, but it has very excellent breeding capacity. So it can produce more fuel than it is burning. On the other hand, the single fluid reactor, it's very much simpler, and it has a low breeding factor. That means it burns more or less the same or more than what it's producing. And then there is another classification which is down here, the fast reactors and the thermal reactors. And we will talk more about that. These are two of the proposals for fast reactors. The Mozart, which is as described by Viktor Ignatieff in 2007, designed in Russia at the Kurchatov Institute. And on the right side, the EVOL European molten salt fast reactor. It is a proposal that is being studied currently, and very recently, at the end of last year, a meeting of the EVOL, they showed this advanced core design, the temperature distribution, which is much better than this from the flow point of view. So some of the advantages of more fast reactors is that the core is extremely simple. It's just an empty tank. There's nothing that can go wrong there. It is extremely stable. And why is it so stable? Well, because the fluid, if it becomes hotter, it expands. And when it expands, it reduces the reactivity. So therefore, by reducing the reactivity, it starts to cool. So it is naturally stable. Some of the experiments, mathematical of course, that have been run, show that the reactor starts to heat up and then cools, oscillates, and it comes to a steady state. And this is what would happen if you suddenly stop all the devices inside the reactor. Like, say, the case in Fukushima, no electricity. It is very stable. It is a breeder reactor that produces more fuel in operation. But the disadvantage is that it has a very long doubling time. The doubling time is the amount of time that it needs a reactor to produce as much fuel as it has consumed. And for the EVOL project, as described in 2008, the doubling time is about 40 years, which is very much longer than the doubling time of the demand for energy. So something else has to be done in order to produce more fuel. Then another disadvantage is that it requires a very complicated chemical processing system. I shan't go into details of this, but it's a diagram of made by David Rodriguez, who is a PhD student at, and I'm sharing the office with him in Orsay. Now I'm going to talk about the thermal reactor, and mostly with the design of Kazuo Furukawa. He created the concept of the mini Fuji, then the concept of the Fuji reactor, and the concept of the accelerator molten salt breeder. So First, the Fuji reactor. What is it? It's a very small reactor. The core would be about here, this size. Very small. And why? The objective is to recover the basic technology, the know-how that was obtained at Oak Ridge 40 years ago. One thing is having the information there. Libraries are full of information, but knowledge really requires that you do things with this knowledge. And this is what is needed to make this little reactor so that we actually know what we're doing and find out, again, all the difficulties. In this reactor, the contents of the reactor core is mostly pure graphite with holes through. 6% of the volume is the liquid that is flowing through. And there is a control by graphite rods, which is, they work the other way around. You increase the reactivity by introducing more graphite inside the core. This is a full view of the Fuji molten salt reactor. In the left side, you have the reactor's core with a 3 containment system. There are 2 places down here where if you drain the fuel, it will go there and it will be completely harmless because the fuel is only produces fission when it is inside with graphite. So if the fuel flows out, it is harmless. It just, when it cools, it becomes like a stone, as we will show. On the right side is the parts of the reactor which are to transport energy and to heat, and this to produce electricity. And this is a description of the Fuji reactor core. It is a small reactor, only 160 megawatt electric. And the idea is that it is so safe, it can be built right next to cities and have very little expenditure in transport of energy, electricity. And this is, it shows the first containment area and the second containment area. Now, here, if anything would happen, you would drain into one of the containers below. And that is the heat transfer unit. So what are the advantages of the molten salt reactor? It is practically impossible to have a severe accident because it is very low pressure. Only about twice the pressure of a car tire inside a steel container. And the molten salt is chemically inert. It does not react with water or air or anything. And the boiling point is about twice the temperature of the operating temperature. So it is very safe. Any excursion going higher temperature, it is safely below the boiling point. And there are many other advantages. I couldn't go spend the time, but I shall point out 2 of them. This is the diagram of the heat change in the reactor. And one of the points is that there is a radioactive gas removal. You inject helium and it removes the radioactive gases that are produced by fission. And this was found at the experiment by the Oak Ridge to remove some other radioactive materials. So if there is any problem, there wouldn't be any gases getting out of the reactor because they're not there. And this has another advantage, that there is no xenon poisoning. This is a phenomenon which was instrumental in what happened at Chernobyl. Xenon poisoning is something that in a normal reactor you have to have an excess reactivity in order to overcome the poisoning by xenon. In this reactor you are removing the xenon, so you don't have to have an excess reactivity. And by not having the xenon poisoning, the reactor can go up and down power, which is something that is not done with normal reactors. They are better operating always at the same power. So it is a reactor that could provide energy for peak need, or during the night when there is less, you reduce the power. And therefore you increase the length of the... And then there is another point, which is this freeze valve. The freeze valve is a valve which is below the reactor, and it is actively cooled by blowing air into an area where the salt is frozen. So if you stop the electricity, you stop this blowing, this freeze valve would melt and allow all the fuel to fall down into the drain tank. And he would make this drain tank designed by passive cooling so that the fuel becomes solid in there. And this would mean that if this reactor had been at Fukushima, nothing would have happened. After the repairing everything around, you remelt the fuel and pump it back into the reactor. So there is safety. The fuel is only critical in the graphite, and the fuel becomes a solid, trapping the radioactive material. There is less nuclear waste. The fuel in the reactor can stay in the reactor permanently for 30 years. And thorium is a fertile material that produces very little actinides. And the molten salt is an ideal media for reprocessing and recovering. And this is a proposal by Furukawa, which is to reprocess the fuel from current reactors by turning these fuels into fluorides, dissolving these fluorides into the molten salt and pushing them into this device. And this device, what is it? At the top, there is an accelerator, which is not there. A very high energy accelerator that throws some protons into the fuel inside there. And it uses a nuclear process called spallation. Spallation is when a particle falls against a heavy ion, a heavy element, it produces a lot of neutrons, 40 neutrons per reaction. It is a very neutron-rich reaction. The reactor itself is not a neutron-rich device. It is an energy-rich device. So in this concept, you don't need a fast reactor to produce more fuel. The fuel would be produced in a device like this, in where a neutron-rich reaction can produce a lot of fuel by irradiating thorium and producing uranium-233, and also by burning the actinides from the reactors that are currently operating. So, non-proliferation and terrorism, no production of plutonium, burning of weapons-grade uranium, and the production of uranium-233. Now, uranium-233 was used for one atomic bomb in 1955. And after that, it was never used again, because it is very bad, very difficult to produce a bomb with it. And the reason is that it is very radioactive. Not the uranium-233, but another uranium which is together with it. And it is very difficult to produce uranium-233 without the uranium-232, which has high electricity, high radioactivity. So therefore, it is very difficult to work with it. You cannot make a bomb with it because you couldn't stay next to the bomb. It would kill you. Or you would have to shield it with such amount of lead that the airplane would take very, very difficult to take off. So it is a very safe kind of fuel. And no fuel fabrication plants, very short economy in the short and long run. So zero nuclear weapons, energy independence for us, and the use of our own thorium devices. We have thorium in Venezuela and in Brazil. So some of the developments, a few comments very quickly. In Europe, there are quite a few countries working, groups there. There are several organizations, as shown there. And all of those institutions are participating in this EVOL development. In Japan, there are several. This is a new proposal by Takashi Kamei. And there is the Molten Salt Forum, which includes 13 countries, and there are several universities, and there's the Fuji reactor, which was designed there. In India, this is another emerging country coming into the molten salt camp. They have, for a long time, a 3-stage project to use in the 3rd stage thorium. It was created by Baba, the creator of the Baba Nuclear Center. Now they are coming into the thinking that the 3rd stage will be perhaps a molten salt breeder reactor. And countries like the US, they have 2 companies, one by flvEnergy. Kirk Sorensen is the man pushing it behind. Transatomic Power, which is a spin-off from the MIT. Some students there work. And there is a Thorium Energy Alliance organization, which is very active in the US. And in Venezuela, we have a small facility which we are actually doing experiments, not with molten salt, not at high temperature. It is a room temperature experiment with liquid fuel, and there are some photos there. And these spectra was obtained about a week ago from the device that is operating there. And the most advanced project is in China. China is definitely moving towards the molten salt reactor, in addition to other projects, in addition to a pebble bed reactor, in addition to fast reactors. They have plans for, they announced plans for 300 million in 2011. And now, very recently, at the Shanghai conference, the Institute for Applied Physics is working with the support of the Chinese Academy of Sciences. And there is a budget, which is this year, 100 million. And it is definitely that they will go into, yes, so this is it. In conclusion, nuclear power is the only technology capable of supplying the world's huge demand for energy. Present-day power solid fuel reactor technology have problems which have made it non-acceptable by society, although they are producing very good service. And there's a worldwide movement in support of the thorium molten salt reactor. The development of different forms of molten salt reactors is recommended as competition will lead to the best technology. And finally, the thorium molten salt reactor is a new technology capable of providing the clean, safe, and cheap energy which is necessary for future development of society. Thank you very much.